Hey there guys, Paul here from the engineeringmindset.com. In this video we're going to be looking more into solenoids and how they work. We're going to look at permanent magnets and how to see their magnetic field. We're going to create an electromagnet from a wire. We're going to be looking at some real world solenoids and we'll also cut one open using some power tools. And finally we're going to learn how to build our own basic solenoid. If you are working with solenoid valves, you're going to want to download the magnetic tool app from Danfoss, who have kindly sponsored this video. The app makes it easy to test that your solenoid valve is working properly and works with both AC and DC versions. You can download it for free for Android and iPhone using the link in the video description below. So we'll start off by taking a look at a standard bar magnet. This is a permanent magnet. You've probably seen these type before. They have their ends marked. One end will be N for the North Pole and the other end will be S for the South Pole. We can use its magnetic field to move other objects. If we imagine this iron nail as a piston in a valve, then we can see that the magnet can be used to move the piston. The problem with this type of magnet is that the magnetic field can't easily or practically be turned off. So in this case the nail will stay attached to the magnet until we physically pull it off. If we place two of these magnets together, we will see that the likewise polar ends will repel each other, but the opposite polar ends will be attracted to each other. If I then place a compass near the magnet, we see that as I move the compass along the perimeter of the magnet, the compass is being affected by its magnetic field, and the compass face will rotate to align with the opposite polar end of the magnet. You'll see it also follows the magnetic field lines. Remember, opposites attract. We can see these magnetic lines if we place the bar magnet down on a sheet of white card and then we sprinkle some iron filings over the top. The iron filings are aligning with the magnetic field lines to create this pattern. These lines always form closed loops and they run from the north to the south. As I mentioned, the problem with permanent magnets is that they are always on and they can't easily or very practically be turned off or controlled. However, we can control an electromagnetic field, and we can generate that with some standard wire. Let's have a look. If we take this standard earthing wire and strip away the outer insulation, we find some copper wires inside. I'm just going to remove this with a sharp knife. Once it's removed, I'll just peel off one of the smaller wires inside. If I place a compass near the copper wire, we see that it has no effect on the compass. However, if I now connect a power source to each end of the wire, we see that as soon as I pass a current through the wire, the current creates an electromagnetic field, and this will change the direction of the compass, just like we saw with the magnet. The electromagnetic field is operating in a circular pattern around the wire. If I place some compasses around the wire and pass a current through it, we see that they all point to form a circle. If I reverse the direction of the current, then the compasses will point in the opposite direction. If we now take the wire and wrap it into a coil, we can intensify the magnetic field. I'll just wrap this around a screwdriver and then compact it until it looks something like this. Now if I connect a power supply to the coil and pass a current through it, we see that the compass will be affected and it now points at the end of the coil just like it did with the permanent magnet. When I move the compass around the perimeter of the coil, the compass will rotate to align with the magnetic field lines. If I reverse the current, we see that the magnetic poles will also reverse. When current flows through a wire, it creates a circular magnetic field around the wire, as we saw a moment ago. But when we wrap the wire into a coil, each wire still produces the magnetic field, except the field lines will merge together and form a larger, stronger magnetic field. We can tell which end the north and south pole will be for a solenoid coil by using the right hand grip rule. This says that if we grip our hand into a fist around the solenoid and we point our thumb in the direction of conventional current flow, that's from positive to negative. It actually flows from negative to positive, but don't worry about that for now. But if we point our thumb in the direction of conventional current flow, then the thumb points to the north end and the current will be flowing in the direction of your fingers. So if we have current flowing in this coil from positive to negative, so from left to right, then the current is flowing through the coil towards us and the north pole will be on the rightmost end. We can check that because the compass will face the opposite direction. Remember, opposites attract. So one compass points north for the coil's south pole and the other points south for the coil's north pole. If we then reverse the power supply so the current is flowing conventionally from positive to negative, So from right to left, we simply flip our right hand over. The current is now flowing away from us in the coil, and our thumb points in the direction of north. Our compass points north to the coil's south pole, and the other points south to the coil's north pole. If we now look at this real-world solenoid valve, we see on the bottom there's a metal valve body, and on the top is the solenoid within the blue box. So let's cut this one open and see what's inside the solenoid. I'll just place this one into the bench vise, and then I'll use the angle grinder to cut it open. I'll make one cut along the front side, and then I'll rotate it and cut down the other side. There's a few sparks coming out because we're cutting through metal on the inside. And there we go, this section has been cut out. If we look inside, we can see it's a pretty basic design with no moving parts. It looks like there's a solid copper ring inside, but that's just from the cutting blade. If we poke at the coil region, we will see it's actually a whole load of small copper wires all tightly packed together. With a little nudge, they will all fall out. Here's a much smaller real-world example without the protective casing. It's essentially the same, just a much smaller design and for a different application. If I connect this to a power supply, we can see that the piston can be pulled in by the electromagnetic field as soon as current starts to flow through the coil. If I cut the power, then the spring will force the piston back to its original position. I can remove the insulation tape to show that it's just a coil. If I then reassemble the solenoid and connect it to a power supply, we see that the piston is moved by the magnetic field and the spring. So now that we know how one works, let's make a very simple one ourselves. I'm just going to use this pen as the core body for the solenoid. I'll just cut this down so it's shorter in length. I'm going to use an angle grinder to cut this for no real reason other than I'm just being lazy and I like using power tools. Now I'm going to melt the ends slightly. I'm going to melt them with a lighter, and I thought I'd just show you this clip of a lighter from our new slow motion camera. This is filmed at 1000 frames per second, which is about 20 times slower. Pretty cool. So I'll just melt the ends with a naked flame, and then press the ends against a solid surface to spread them out. I'm doing this because I want the ends to protrude slightly, which will make the coils easier to wrap. Now that I've melted and shaped the ends, I just need to drill through the excess in the center to allow the piston to oscillate. I'll also just file it down so it's nice and smooth and the piston doesn't catch on the edges. For the piston, I'm just going to use the iron nail. Now we need to wrap the coil. I'm going to use some 26 gauge or 0.4mm enameled wire which I bought online. I'll leave some links down below for where to get that. So we simply want to wrap the copper wire as tight as possible from one end to the other. When we do that, we should end up with something like this. Then we need to wrap it a few more times in opposite directions to make it stronger. 3 or 4 wraps is probably fine. I didn't count the number of turns for this one as I'm just making a quick example for you. Once it's fully wrapped, we can just cut the wire and free it from the drum. Then we want to just use some sandpaper to remove the enamel, which will give us a better electrical connection. So if I place my iron nail concentrically within the coil, but not fully within, we see that the nail piston is pulled inwards by the electromagnetic field as current passes through it. If we were to place a spring at the end, it would return to the original position. If we place the piston fully within the coil and then apply a current, the magnetic field will move the piston, and we could use this to provide a pushing force. Again, if there was a spring on the far end, then it could be returned to its original position. I just want to remind you to download the magnetic tool app from Danfoss for free using the link in the video description below. Okay, that's it for this video, but if you want to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, and of course, theengineeringmindset.com.